Sorry. I'm Kazuteru Umetsu, Senior Manager of Asahi Kasei Europe, and have involved developing not only lithium-ion batteries, but also lithium-ion capacitors. Today, I'd like to share our knowledge and insight about high ionic conductive electrolytes. So regarding the timeline of this session, I want to give my presentation for 25 to 30 minutes, followed by Q&A and pre-discussion for 10 to 15 minutes. Okay, so this is the outline of this presentation. So I'd like to introduce our company, Asahi Kasei Corporation first, then our high ionic conductive electrolyte, acetonitrile-containing electrolyte. After that, the comparison between acetonitrile and esters, which are known as high ionic conductive solvents, will be introduced. Finally, we succeeded in the proof of concept for the acetonitrile technology with our partner Lithium-Works. So Asahi Kasei is a Japanese conglomerate and consists of three business sectors: material, homes, and healthcare. In material sector, you might have heard our separator brand High-Power and CellGuard for lithium-ion batteries. So we were founded in 1922 in Nobeoka, Japan. The turnover in 2023 was 17.9 billion euros, almost the same as $18 billion. We operate across 88 sites in 20 countries, and employees are almost 50,000. As some of you here today may know, our honorary fellow, Dr. Akira Yoshino, is one of the inventors of lithium-ion batteries, which have now become indispensable in our lives, including smartphones, PCs, and electric vehicles. So lithium-ion batteries have enabled the development of modern portable electronic devices, and more importantly, are playing a key role in promoting sustainable energy use. Okay, so let me move on to the next topic, our technology, acetonitrile-containing electrolyte. So in recent years, there has been an increasing demand for high-power lithium-ion batteries in EVs and other applications. For example, the benefits of high-power levels in EVs include low-temperature operation, fast charging, reducing heat generation, and improving energy efficiency, and so on. So there are several approaches to designing such high-power levels. Electrodes, separators, and electrolytes have their own items to improve the battery performance. Today, I'd like to focus on electrolytes, especially in high ionic conductive electrolytes. So this graph shows the viscosity and relative dielectric constant of the solvents used in lithium-ion batteries, which affect the ionic conductivity. In order to increase the ionic conductivity of the electrolytes, it is necessary to decrease the viscosity of the solvents and increase the ionic dissociation. In other words, the upper left area of the graph is expected to show high input-output characteristics as an electrolyte for lithium batteries. From this perspective, H2O is ideal solvent. However, its narrow potential window makes it difficult to use it as a solvent for lithium-ion batteries. Ethylene carbonate, EC, has a very high dielectric constant, but because of its high viscosity and its melting point, it is usually used as a mixed solvent with linear carbonates. Acetonitrile is one of the promising solvents to enhance ionic conductivity and realize high-power lithium-ion batteries. So in recent years, esters have been used to increase the ionic conductivity of electrolytes. Methyl acetate, ethyl acetate, and other linear esters are located lower left side in the graph and have lower viscosity than linear carbonate. As mentioned on the previous page, acetonitrile is a promising solvent, but it is easily reduced when in contact with lithium metal. Dr. Matsuoka and our team succeeded in using acetonitrile as a solvent by using the combination of vinylene carbonate, VC, and ethylene sulfide, ES. These right side of two photos were taken to investigate the stability of the acetonitrile electrolytes against lithium metal. And lithium foils were dipped in 1.3 molar of LiPF6 in acetonitrile electrolyte. As you can see, the electrolyte turned brown when only VC was applied as additive. But when using the combination of VC and ES, the color didn't change even after 7 days at 50 degrees C. So in the table, our standard acetonitrile-containing electrolyte components are described. LiFSI and LiPF6 are used as lithium salt. Acetonitrile and other linear and cyclic carbonates for solvent. BC and ES are for SI formation additives. And nitrogen-containing heterocyclic compounds to stabilize LiPF6 are also used. We usually arrange the formulations according to our customer's design and their request. So both acetonitrile and esters can realize high ionic conductivity, and I would like to introduce our experimental data comparing them next. So as you might know, some lithium-ion battery manufacturers are using esters to improve C-rate and low temperature performance. But there might not be a study comparing the battery performance of acetonitrile and esters. So in this test, 55 metric percent of acetonitrile and there are 3 kinds of esters: methyl acetate MA, ethyl propionate EP, and ethyl acetate EA were used. And ethyl methyl carbonate EMC was used as a control. The electrolyte consists of 1 molar of lithium FSI and 0.3 molar of LiPF6 in EMC and EC solvents with 7 metric percent of additives. Their viscosity and ionic conductivity were measured at 25 degrees C, and the results are shown on the right side of the table. Ester showed higher ionic conductivity than EMC, and acetonitrile is the highest in this test. Among the esters, MA shows the highest ionic conductivity, which has the shortest carbon chain structure among the esters used in the test. So next, partial evaluation were carried out with LFP graphite system using the electrolytes evaluated in last page. 8 stacked pouch cells were assembled, and its photo is here. First, here are the results of the C-rate performance at 25 degrees C. After charging at 3.6 volt, discharged at 0.3 C, 0.5 C, 1 C, 2 C, 3 C, and 5 C to 2.0 volt. Acetonitrile showed the best performance among these solvents, and the esters were better than EMC. Similar to the trend in ionic conductivity, among the esters, MA was the best, followed by EA and EP. Okay, acetonitrile showed the best performance among these solvents at 25 degrees C, but its performance was further enhanced at the extremely low temperatures of -40 degrees C. These graphs are discharge curves at 0.33 C and 0.5 C from 3 to 6 volt to 2 volt. All esters improved low temperature performance, but acetonitrile even more. Cycle performance was evaluated at 50 degrees C. The conditions were 1C 1C from 3 to 6 to 2 volt, and 0.2C 0.2C every 100 cycles. As you can see, all electrolytes showed stable performance for 300 cycles. So in this way, it was found that esters and acetonitrile have the potential to significantly improve output characteristics due to their high ionic conductivity without compromising the durability of existing carbonate electrolytes. Okay, finally, I'd like to introduce the proof of concept results of acetonitrile containing electrolyte. Taking advantage of its high ionic conductivity, acetonitrile contributes to improving C-rate performance, fast charging, and the low temperature performance of lithium-ion batteries. These improvements will make it possible, for example, to reduce the size and cost of battery packs. In addition, acetonitrile makes it possible to realize thicker electrode without giving up the C-rate performance, which contribute to increase the energy density and reducing material cost. So in this way, acetonitrile technology contributes to a low carbon society by increasing the value of lithium-ion batteries with its high ionic conductivity. So last year, Asahi Kasei issued a press release announcing that we had successfully completed proof of concept using LFP graphite energy type 18650 cylindrical cells with lithium works. In the results, our acetonitrile containing electrolyte improved low temperature output and high temperature durability at the same time. Please look at the graph on the left. Low temperature performance was evaluated, and the discharge capacity of the standard carbonate electrolyte at -20 degrees C set at 100%. Then the relative discharge capacity at -30 and -40 degrees C are shown respectively. Standard carbonate electrolyte could not discharge at 10 C below -30 degrees C, but acetonitrile-containing electrolyte could even at minus 40 degrees C. So next, please look at the graph on the right. Cycle performance was evaluated at 0.5 C, 1 C from 3 to 6 volt to 2 volt at 60 degrees C. Acetonitrile-containing electrolyte showed higher capacity retention than standard carbonate electrolyte and achieved double the life cycle. Cycle durability at 23 degrees C and 45 degrees C were also evaluated, and a similar trend was confirmed as in the 60 degrees C evaluation. Energy type cells were evaluated, but power type cells were also evaluated. Low temperature performance of LFP graphite 26650 cylindrical cell were tested from minus 20 to minus 40 degrees C. The graphs above show the result of acetonitrile, and below for the standard carbonate electrolyte. Each graph shows the discharge curves and the heating behavior of the batteries. It can be seen that the acetonitrile-containing electrolyte suppress the voltage drop and internal heat generation of the batteries. In addition, while standard carbonate electrolyte was not able to discharge at minus 40 degrees C, acetonitrile made this possible. Next, simulation tests of an actual battery pack were evaluated at minus 30 degrees C. The same LFP graphite power type 26650 cylindrical cell on the previous page were used in this test. The graph on the left, the yellow line shows the current pattern per cell of the 12-volt auxiliary battery pack, assuming 5 in series and 12 in parallel. And the blue and the gray lines are the corresponding voltage curves of the acetonitrile and the standard carbonate electrolyte. The lowest operating voltage was 1.6 volt per cell, and both electrolytes passed this condition. Next, so please look at the right graph. We conducted tests with the number of parallel cells in the battery pack reduced from 12 to 10. The current per cell increased, which caused standard carbonate electrolyte to fall below the lowest voltage limit of 1.6 volt. On the other hand, acetonitrile-containing electrolyte remained over 1.6 volt thanks to its high ionic conductivity. In this way, the high ionic conductivity of acetonitrile contribute to the size and cost down of the battery pack. Okay, here is the conclusion of this presentation. Acetonitrile improved ionic conductivity and realized superior output performance than esters such as Ma, Ea, and Ep over a wide range of temperatures. And the proof of concept was successfully completed and realized both low temperature performance and high temperature durability in LFP graphite cylindrical cells. This will bring a technological impact not only on cost reduction, but also realization of higher energy density. future focus will be on scaling up this technology for commercialization, and collaboration with industry partners is essential to accelerate the development and deployment of these advanced lithium-ion batteries. Okay, so by the way, so let me introduce LICT-FSI as a next generation lithium salt. For example, a linear imide salt such as LiFSI and LiTFSI increase the ionic conductivity of electrolytes and improve low temperature performance and durability of lithium-ion batteries, but are known to corrode the aluminum current collector under the high voltage conditions. To prevent this, it is common to mix a fluorine source such as LiPF6 into the electrolyte to form a protective layer on the aluminum foil. However, lithium CTFSI, this cyclic amide salt, does not cause the aluminum corrosion, even at a higher voltage, and can be used as a sole salt. So this means that there is no need to use LiPF6, which is unstable to heat and has the potential to achieve high temperature and high voltage that were previously not possible. Okay, finally, I'd like to express my sincere gratitude to Lithium Works for their support in the proof of concept of the LFP cylindrical cells, and to our colleagues in Japan and Germany. Thank you very much for your kind attention. Okay, so thank you very much for joining my presentation. So are there any questions or comment? And free discussion are welcome.
Thank you for your nice presentation.
Yeah, thank you.
And the information that you gave us. I have a question about the window of the charging limitation for the for a battery system with acetonitrile electrolyte. I mean, for example, in some cases, in some lithium-ion batteries, we say that the operation temperatures are a limit. For example, minus 15 or minus 20 up to minus, for example, 50. But the limitation for the charging is something different with this operation limits. We need some I mean enhanced situation to charge the battery in for the next cycles. Have you something related to this subject?
Yeah, thank you very much for your nice question. So for the limitation of the temperature, we tested from -40 to 6 degrees C. It's the machinery issue. Our climate chamber can work from -40 degrees C, but under the temperature, nitric containing electrolyte can charge the batteries.
So the temperature limit is wider than the operation temperature?
Yes, so I think so acetonitrile can improve low temperature performance. So so it can wider their temperature range. So especially low temperature.
May I ask another question?
Yes, please, thank you.
When we talk about the conductivity in in ion conductivity inside the battery, sometimes we remember that, for example, some polymers that can enhance as an additive, or in solid state batteries as an electrolyte that can enhance the ion conductivity inside the battery. So when we use acetonitrile, can we use some additives? Is it any? Have you done any study about it, about additives that can enhance this kind of ion conductivity inside the electrolyte?
So may I confirm your question again? So additives means polymer additives, right?
Mostly, mostly.
Mostly. So I haven't tried polymer additives, but so yeah, okay. So I've I've read the patent that apply the combination of acetonitrile and polymer electrolytes and enhance their output input characteristics. Yeah.
Thank you. Thank you very much.
Yeah, thank you very much for your question. Yeah.
Hi, Kazuteru, can you hear me?
Yeah, yes.
Hi,
Hello,
hi.
Jason.
Yeah, it's great. It's great presentation. So I have a few questions. The first question is, when you say that the next step is the scale up, what do you see is the major challenge for the scale up of coating nitride based electrolyte? And the second question is, your electrolyte improve a lot of, temperature range in low temperature. How about in the high temperature range? And the third question actually, what do you think that this electrolyte perspective for the other batteries, such as the lithium metal or silicon-based electrolyte, silicon-based battery?
Okay, thank you very much for the nice question. So for the first question, so what is the challenge for the scaling up of technology? So in this page I explained, so we need to arrange the electrolyte formulations based on our customers. So creating good SEI on the surface of anode is very important to manage our technology. So that's why we need to arrange the additives and additives and solvents according to our customers. So that's why. So that is kind of challenges to realize our technology to our customers. Yeah. And for the next question, the high temperature limit. So I think the high temperature limit is same as the carbonate-based electrolyte. So many carbonate-based electrolyte upper temperature limit is about 60 degrees C or so. So in this slide, so we realize 60 degrees C temperature limit. Yeah. So I think the temperature limit is same as carbonate-based electrolyte. And could you again the third question, please?
Yeah, the third question is, what do you think that this electrolyte formulation, can it apply to other kinds of batteries, for
Okay.
example, the lithium metal or silicon-based batteries?
Yeah, okay. So I think lithium acetonitrile can work both lithium metal and the silicon containing anode. Yeah, but I think silicon metal and lithium metal, silicon containing anode and lithium metal itself has own challenges to realize commercialization. Yeah.
So basically, you have to work with specific customers to trying to add different additives so it can form the stable SEI to be able to make the batteries that with the right properties.
Yeah, that's right. Yeah.
Okay. Thank you, and I would certainly like to follow up with you for this. Is kind of very promising because we do have we actually also make electrolytes, and the customers specifically, I mean, think that they want to non-carbon based solvent for their batteries.
So may I ask your your company?
Yeah, our company is Automat Solutions.
Automat Solutions. Thank you.
Yeah, we are based in California, in Silicon Valley.
Okay. Thank you.
Hey,
Thank you.
Can I ask two questions, Kazuteru?
Yeah.
Yeah, thank you for your very nice presentation.
Yeah,
I never thought the acetonitrile can be so effective because normally it was used in the capacitors. Two questions. What is the flammability of this electrolyte system, like the acetonitrile base? That's one question. The second question is, have you guys patented this electrolyte already?
Yeah, thank you very much for the next question. For the first question, so we conducted a safety test, both acetonitrile containing electrolyte and carbonate-based electrolyte, and their flammable behavior were the same, and their flammable performance, flammable behavior, and their temperature. Temperature behavior were the same. Yeah. And the gas generation were also the same as the carbonate-based electrolyte. And for the next question, patent. So we applied not only electrolyte itself, but also lithium battery itself. So formation protocols and other impurities of the batteries and so on. So we applied a wide range of patent. Yeah.
Okay,
so,
thank you.
Yeah. Thank you.
Hello, can you hear me?
Oh, yes.
Yeah. Thank you for your presentation, really informative. Quick question. What were the voltage ranges you were utilizing for the AcN based cells?
Okay. Thank you for the question. So I introduced LFP graphite system, and it's suitable for acetonitrile. But we perform it in NMC system. So it means 4.2 volt in the 4.2 volt system. And in the system, acetonitrile can work. And but the suitable cathode is LFP for NMC material. So gas generation is one of the problem. But a smaller size cell, acetonitrile, can perform well.
Okay, I was looking at the lower cutoff voltage to see if you were, let's say, raising that in order to help the AcN stability.
Yeah, that's right. So voltage limitation can reduce the gas generation. Yeah, thank you.
Okay.
Okay, so if there are no questions, so I'd like to close my session. Okay. Okay, thank you very much for joining.